Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of this video is the diesel cycle, and the section in the textbook is section 9.6. Here are the learning outcomes for this video. At the end, you should understand the relationship between an actual and an ideal diesel cycle. You should be able to derive the diesel cycle efficiency using the cold air standard assumption, and you should be able to calculate the properties at all four states of an ideal diesel cycle. So first I want to go ahead and discuss the ideal diesel cycle. It's fairly similar to the Otto cycle, but there's one important difference. So first there's an initial compression step. Usually starts from a relatively large volume and we go up to a higher pressure. So we'll call that point 1 and point 2. Now this is where it deviates from the Otto cycle in that the difference between a diesel cycle, which is a compression ignition and a spark ignition system, is that instead of there being a spark and a very, very quick burning of the fuel, which causes a high increase in temperature without much change in volume, is that what happens in the diesel cycle is only the air is initially compressed, and then the fuel is sprayed in slowly, relatively slowly. And as it is sprayed in, it combusts instantly because it's at a fairly high temperature, and the piston moves down. And this occurs more or less at a constant pressure. And so this goes sort of like this. In the ideal cycle, we're going to say that it happens at a constant pressure, 2.3. which is somewhat larger volume, but it's not the entire displacement volume. At that point, the fuel is stopped, no longer sprayed in, but it's still at a high pressure, and so it will continue to expand down to its final volume at bottom dead center, which would be 0.4, and then the exhaust stroke occurs. So therefore, this is the Q in step when the fuel is sprayed in. This is the Q out step right there. But there's actually the power stroke occurs in 2 to 3 and 3 to 4. Now the difference, the area in here is still the net work for this cycle, but there's a little bit difference in that power part of the cycle. The TS diagram actually doesn't look much different. So again, we start at point 1, which is at a relatively low temperature and entropy, isentropic compression 2.2, and then this is that constant pressure stroke where heat is added. So we increase the temperature and the entropy up 2.3. And then going from 3 to 4, it drops down. It's a power stroke. It's isentropic to 0.4. And then we reconnect as well. So it looks very similar to the Otto cycle. The only difference is that this step right over here, pressure is a constant along that step there. And volume is a constant along here. So the slopes of those lines are somewhat different. That's a subtlety you don't have to worry about too much. So the TS diagram looks very similar. It's the PV diagram. It's a little bit different between the diesel cycle and the Otto cycle. All right. So I want to talk about the thermal efficiency for using the cold air standard. And so we're going to end up deriving this equation I show at the bottom. So first, let's just remind you what the thermal efficiency is. Thermal efficiency is, well, the net work over the heat that I put in. And I can rearrange that to 1 minus Q out over Q in, where now I've got the Q's on a per mass basis. And so again, remembering, here's my diesel cycle. I'll just kind of draw it up quickly on a PV diagram. Just like that. 1, 2, 3 to 4. Okay. And the Q in step, which is right there, which is going to be 2 to 3, okay, which is going to be that term right there, is going to be a little different than what we had before. With the Otto cycle, we had a CV term. Well, now this is at a constant pressure. And so Q in, which is the step from 2 to 3, is actually going to be CP T3 minus T2. Okay. Now here's the Q out step, 4 to 1, and so Q out, similar to the Otto cycle, is going to be a CV T4 minus T1. And so we have a CP and a CV, and so that kind of changes the efficiency equation somewhat. And so we end up needing to kind of do a little bit more algebraic rearrangement. The book has the details. The details don't matter too much, but there's something called the cutoff ratio, which is R sub C, and it's defined as V3 over V2. So it's this volume right here divided by that volume. So it's sort of the partial expansion that happens during the fuel addition. And with this extra parameter, R sub C, we end up with this efficiency equation I showed at the bottom. It's a little bit more messy than what we had with the Otto cycle because we've got this cutoff ratio term in addition to R. So R is still the compression ratio. So R is still defined as the volume of 1 over the volume of 2. So there's two terms that you need for the diesel cycle. You know the cutoff ratio and the total compression ratio. And so here's the equation for the thermal efficiency using the cold air standard. Just a little bit about the compression ratio. So here we've got a plot of the efficiency as a function of the compression ratio. The general form we saw is similar to the Otto cycle, where the efficiency increases with higher compression ratios. We have a little bit of diminishing returns as we get to higher compression ratios. And this little shaded region shows typical compression ratios for diesel. And one of the things I want to notice is that this comes up to the low 20s over here, whereas the Otto cycle was actually, the maximum was like 10 or 11. So diesel cycles are able to accomplish a much higher compression. And that's because during that compression stroke, to go back and remind you, during that compression stroke, there's not air and fuel in there that I'm compressing, so I don't have to worry about pre-ignition. So it can be really, really hot, and that's why when I first spray the fuel in, it ignites instantly during this 2 to 3 step. So we have really, really high compressions. It gives us a little bit higher efficiency. You see the efficiencies up here can be theoretical ones of 60 or 70%. A couple other things I just want to mention. Here's that R sub C value, the cutoff ratio. And this actually decreases a little bit as you increase the compression ratio. And R sub C equal to 1 is actually the same as the Otto cycle. And if you draw off the cycle, you see how that happens, because this is 0.1, 2, 3, and 4. Remember, the compression rate, or sorry, the cutoff ratio, R sub C, is this volume over that volume. And as I move that point closer and closer to 0.2, you realize I'm starting to approach the Otto cycle. And that's why this top line corresponds to the Otto cycle. But the decrease with cutoff ratio isn't all that much. And the fact that you have a cutoff ratio is simply just the nature of the way that diesel engines are constructed. All right, so what I'm going to do is go through an example here. And here's the example we're going to solve. We've got a 5-liter diesel cycle. So the diesel engine, the total displacement volume is 5 liters. We have a compression ratio of 20, a cutoff ratio of 2. We got our inlet conditions at around atmospheric, 100 kPa and 25 degrees Celsius. We're told that the net work is 100 kilowatts when it's operating at 3,600 RPMs. And so we're going to go ahead and find out what the thermal efficiency of this cycle is. So let's start just sketching up a PV diagram to remember our states. Here's our diesel cycle, 1, 2, 3, and 4. And so we know everything over here at 0.1. And so what we're going to do is going to again kind of move through the cycle. And so we're going to go from 0.1 to 0.2. Now, one of the things is that it's really good to just go ahead and not assume a cold air standard for this if you can, because with these really high compression ratios, you have really high temperatures. And so with these large temperature changes, constant heat capacities are not necessarily the best assumption. So let's go ahead and do it the way that we did it before. We had a variable heat capacity, which was that V1 over V2, which is the compression ratio, would be the relative volumes VR1 and VR2. And so remember, the relative volumes are functions of temperature. I'm going to get those on table A14. So go to table A14. So I'm going to look up the value of VR1, that is 25 degrees Celsius, or 298 Kelvin. And that value off the table is 631.9. And that is over VR2. And so now I can go ahead and solve this equation to find out what VR2 is. And VR2, if I do that, is 31.6. And that tells me that T2 is equal to 926 Kelvin. And I just mentioned, that's a pretty hot temperature. That's the point at which this compression stopped, because I had such a high compression ratio. And this is why diesel cycles can't have fuel in there initially. You would have pre-ignition if you reached that high of a temperature, if you had an air-fuel mixture already. All right, so now we're at 0.2. And what we know is we know the net work. We actually know the area inside here. And so if we want to find out the efficiency, I need to figure out how much heat is added in step 2 to 3. And I'm given an extensive value. The net work is 100 kilowatts at 3,600 RPMs. And so what I would like to find is how much work is done per cycle. And so in order to do that, we're going to just use some ideal gas relations. And so we'll start off and find out, well, what is the mass? And so what would be the mass of for example, just a single cycle over here? So we'll just go and use the initial conditions of 100 kPa. And our total volume of 5 liters, or 0.005 cubic meters. And then I'm going to divide that by RT, so 0.287 is the value of R. And then T1 is 298. P98 Kelvin. And so that's going to go ahead and tell me the mass in a single cycle. That would be 0.00585 kilograms. So that happens in essentially just the volume of the engine at one point. And so if I want to know how much material is moving through, well, it's at 3,600 RPMs. And so what we're going to do is we're going to go ahead and remember that the amount of mass that actually moves through is going to be 1/2 of that because of the exhaust stroke. So we're going to take this and multiply it by 1,800. It wouldn't give us what our total mass is. And so if I take that mass and multiply it by 1,800, I get 10.52 kilograms, and that's how much goes through there per minute. So 10.52 kilograms per minute. So now I can go ahead and determine what the net work is, excuse me, on a per mass basis, because I've got my 100 kilowatts or 100 kilojoules per second, and then my mass flow rate of 10.52, and that is kilograms per minute. Oops, go back. And so I need to go ahead and multiply that by 60 seconds per minute to get my units to work out, to get my minutes and seconds to cancel out. And then I find out that the net work on a per mass basis is 570 kilojoules per kilogram. Right, so now I've got W net, an intensive value of 570 kilojoules per kilogram. All right. So now what we're going to do is we're going to keep moving through. We want to go ahead and find Q in on a per mass basis, which is 2 to 3, which means I need to know the enthalpy values at that point. I know what everything at point 2, so I've got T2, which is 926, and I know that the volume is 1/20th. So I'm going to have to get it over to point 3. So let's go ahead again. We're going to be using some ideal gas relations. So let me again sketch up my PV diagram just to remember what it looks like. 1, 2, 3, and 4. And so what we can do is we want to go ahead and figure out what point 2 is relative to point 1. So first let me go ahead and find out what my intensive volume is at point 1. That's going to be R T1 over P1. I have those initial conditions right there. So let's go ahead and do that. 0.287. T1 was 298. And divide that by my initial pressure of 100 kilopascals. So my initial volume in there is 0.855, and that's meters cubed per kilogram. And so then I can go ahead and find out what V2 is, and V2 is just going to be 1/20th of that, is V1 over 20, because that's what the compression ratio is. And so that right over there is going to be 0.04276 meters cubed per kilogram. And then I can get up 0.3 using my cutoff ratio of 2. So I can go ahead and multiply that by 2 to get what V3 is. V3 is 2 times V2, and that's right there, 0.0855 meters cubed per kilogram. So now I know what V3 is. And the other thing I'm going to know is that this is at a constant pressure. So I need to go ahead and find out what that pressure is, and pressure at 3 is the same as 2. So P3 is equal to P2, and I know everything at P2. That is R T2 over V2. We calculated V2 previously on the previous slide. The V2 I just got at that point right there. So let's go ahead and do that. 0.287, and that was 926 we had from the previous slide. V2 0.04276, and that's going to go and give me my pressure at point 3 and point 2, so it's 6215 kilopascals. And so then I can now go ahead and find out what T3 is, which is what I need to go ahead and find out what my enthalpy is, because T3 is going to be P3 V3 over R. So if I put 3 there, I go ahead and plug in those values, I get 1851 Kelvin. And now I'm going to go to table A14 using that temperature of 1851 to go ahead and find my enthalpy value of H3. And so H3 from there is 65.3 kilojoules per kilogram. So that's my value of H3. And my QN, if we go back before and we had our temperature at 926, we can go ahead and use that to find our value of H2, again using the table A14, that is 961.24 kilojoules per kilogram. So now we've got all those values. Let's go ahead and find out what Qn is. Qn is going to end up being equal on a per mass basis of 2065.3 minus the first one, which is 961.24, and that gives me Qn at 1104 kilojoules per kilogram. So there's my W net, and there's my Qn. So let's go ahead and find out what our efficiency is. I'll just do that over here in the corner. Thermal efficiency is 570 over 1104, and that we find out is equal to 51.6%. So there's the thermal efficiency of my diesel cycle. Alrighty. So kind of done a little bit differently than what we did before in the Otto cycle, but we were given an extensive value right up here. So we use these ideal gas relations and our variable heat capacity isentropic compression to go from 0.1 to 0.2. Alrighty.